Good afternoon. My name is Łapińska. I'm from Warsaw University of Technology, and I am very pleased to give you a talk today about carbon filler influence on thermal, EMI shielding, and electrical properties of polymer-based nanocomposites. My presentation outline is as follows. So first of all, I will give you a short introductory information that will be a basis of our investigation's motivation. Then I will describe you shortly samples and describe the results concerning on EMI shielding, thermal conductivity, and electrical conductivity. So we can start. So modern electronics is characterized currently by progress miniaturization, high density of electronic elements packaging, and high power density. This issue makes that we need to protect our devices against electromagnetic interference because all of electronic elements emits the radiation, and if not protected, it may interfere with each other and cause the malfunctioning. The other issue is the protection against the overheating, which is a quite complex and severe problem, because probably there is nobody that not influence the overheated laptop or overheated phone or other electronic elements. But stop here for a moment to describe the phenomena that we are describing, the protective behavior against these two issues. Yes. So first of all, we are using the electromagnetic shield against the electromagnetic interference. And what does it mean? It means that if we direct the electromagnetic wave on the material that should be a shield, that material can transmit the radiation, and then we are not talking about, we are not observing the shielding effect, but it can also reflect the wave, it can absorb, or we can observe the multiple internal reflection. These two phenomena consist of total shielding effectiveness that we measure in decibels. And 10 decibels mean that our materials is able to block 90% of all incident radiation passing through that material. 20 decibels means 99, and so on. Yes. If we are talking about shielding and the materials to shield the electromagnetic interference, we need to remember that specific material can have different characteristic, the shielding characteristic in the different frequency ranges. So in the case of the investigation we have carried out, we carry out our measurements in the frequency range from 2 to 30.5 gigahertz. So that means that we cover band SE and X, that is usually used for wireless communication. In case of the thermal management, we use usually the materials with, for example, high thermal conductivity or a high heat dissipating behavior. Such features possess the thermal interface materials, but the thermal management is quite or it's not quite. It's a very complex issue, because we need to take into consideration not only the heat transfer outside the device, but we need to care about the thermal resistance of the materials we use, thermal interface resistance, the boundary resistance, and so on. So therefore, we still don't have the perfect heat management against the overheating, unfortunately. But as I said, modern electronics requires the protection against these two phenomena, so electromagnetic interference and overheating. And currently we are using separate solution. There's a separate solution if we want to protect either for electromagnetic interference or either overheating. So the motivation of our investigation was to combine these features into one materials. Yeah. So if we combine, we can obtain, first of all, a low number of elements, which is crucial, for example, in space or airborne that suffers from weight, and we can have low number. If we have a lower number of elements, then we have a lower weight, and so on and so forth. So this was the main motivation of our investigation. And the material that can possess multifunctional properties are the polymer nanocomposites. And the polymer nanocomposites can be manufactured by different methods, but in case of our investigation, we have used a very simple method. We mixed and we manufactured the pre-master batch based on the polymer and nanofillers in form of powder. So 2 fraction was powdered. Then we hot press into specific shapes, and this was the main method of the production of our samples. And we have manufactured different types, of course, of nanocomposites, but here I want to show you 2 types of them, both based on the fluoropolymers, because they have the improved basic performance, what is favorable in the airborne and space industries. Yes, so that's why the fluoropolymers, and we choose 2 types: stiff, in this case the PVDF, and flexible one, THV. And we mixed our powdered polymers with the graphene nanoplatelets, with carbon nanotubes, multi-walled carbon nanotubes, and we have mixed them all together. So in case of the results that we obtain, so let's start from the PVDF based on the with the graphene nanoplatelets. So first of all, the dominant shielding mechanism that we observed here was the absorption, because as you see here on the left, you see the total shielding effectiveness, and on the right the reflective component of that shielding effectiveness. And if you compare the values, it's obvious that the major component is the absorption, because we neglect the multiple internal reflection, because we have the electromagnetic shielding suppresses 15 decibels, and in that case we can neglect that internal reflection. The dominant shielding mechanism is absorption. Maximum value that we have obtained was almost 40 decibels. That means that our materials is able to block 99.9 9 two nines after comma. Total incident radiation for 20% of graphene loading. And what is important, we observe here also the saturation effect. So if we add more graphene, then any shielding will decrease simply. In case of the flexible, this flexible alternative of composites, we have not observed the saturation effect. The saturation effect was observed for graphene series, but was not observed for the mixed series, so for graphene and for multi-volt carbon nanotubes, we haven't observed also the synergistic effect in case of the mixed series. The biggest value, the shielding effectiveness value, was observed for the graphene nanoplatelets only series, and it was 23 decibels for 10% of graphene loading. Then we test, I haven't mentioned it, we have tested different types of the multi-volt carbon nanotubes to choose the best for the third mixed series, and here we obtain the best value for the carbon nanotubes of diameters from 10 to 20 nanometers, and that kind of the carbon nanotubes were used in the mixed series. And in case of that carbon nanotube series, we obtained the maximum value of 8 decibels for only 1% multi-volt carbon nanotubes, and mixed series reached 17 decibels for 9% of graphene and 1% of carbon nanotubes. Here, for all the series, we observe the main shielding mechanism as absorption. So the graphene and multi-volt carbon nanotubes favors the absorption as the shielding mechanism, and it's very good and favorable as well for the airborne and space industries. Yes. Then we'll go further to the thermal conductivity. Here we obtain really good because suppresses 5 watt per meter Kelvin thermal conductivity for PVDF-based and graphene nanoplatelets composites. That gives almost 3000% thermal conductivity enhancement if we compared it with the bare polymer. No percolation threshold is observed here. More the linear behavior with no sign of the saturation effect. So if we improve, for example, the manufacture method on something like that, we can obtain here even bigger value. Yes. In case of the flexible alternatives, we have obtained a slightly lower results, but still for graphene series we obtain over 800% of thermal thermal conductivity enhancement, and that maximum thermal conductivity reached 1.665 watt per met Kelvin. So it's quite also quite good. As for the polymer composites, which are usually the thermal insulators. In case of the graphene nanoplatelets and multi-walled carbon nanotubes, we observe the saturation effect and almost 700% enhancement of thermal conductivity. And again, here we also, same as for the electromagnetic shielding, we haven't observed here the synergistic effect, and it's very good and clear when you compare the values that we obtain for loading of 35% of graphene nanoplatelets. This series with just graphene nanoplatelets exhibit higher thermal conductivity with same loading plus 1% of multi-walled carbon nanotubes. In case of the electrical conductivity and resistivity, we use that method in dual functionality, because first of all, that's what you see on the figure 6. You see the results of the sheet resistivity of the PVDF, so stiff version of our composites, and that sheet resistivity using modified Van der Ploeg method may also allow us to assess the filler dispersion in the matrix. So the sheet resistivity made in that form may be also a good indicator of the filler distribution in the matrix. We have also carried out the regular electrical conductivity measurements, and here we obtain almost 40 Siemens per centimeters for the best, and here again the best value was obtained not for the highest loading. In case of the THV, we measure the electrical conductivity and resistivity only for graphene nanoplatelets. Here, unfortunately, we obtain. Unfortunately, it depends. Or fortunately, we observe the lower value of electrical conductivity, only 1.49 Siemens per centimeters, and it can be drawback, but it can be also advantage. It depends on the final application we want to use, because sometimes the electrical conductivity is not desired in the final application. So such results is also a good result. We observe here as well the saturation again, but it need to be further explained, because we haven't fully explained such behavior here. Okay, to shortly sum up everything. So graphene as a filler provides the absorption as a main shielding mechanism. In case of the stiff composite, we obtain the maximum value of total shielding effectiveness of almost 40 decibels. For flexible composites, it was 23 decibels. Thermal conductivity that we have obtained for stiff version is impressive, because it surpasses 5 watt per met Kelvin and giving almost 3000% enhancement compared to the pure polymer. So it's a really worth mentioning value. For the alternative, we obtain a slightly lower a lower thermal conductivity, but still giving and providing over 800% of enhancement. In case of the electrical conductivity, these two versions show the PVDF-based composites is electrically conductive quite well, but the THV is the weak, very weak electrical conductor. But as I said, it may be also an advantage in other application. Carbon nanotubes, on the other hand, also provide the absorption as the main shielding effectiveness mechanism. 1% of the carbon nanotubes gives the 8 decibels of shielding effectiveness, while with the graphene nanoplatelets it reached 17 decibels, and no synergistic effect was here observed. Yes, the thermal conductivity in this case was comparable, let's say, to the graphene-only series. And that's all for my side. Thank you very much for your attention. And if you have a question, please.